Hello, dear listener. I'm so glad we found this quiet space together tonight. Wherever you are, allow the edges of your day to soften and the light around you to become a gentle, inviting dim. Think of this as a slow, quiet drift, a journey taken not through distance, but through wonder. Tonight, we're slipping past the familiar lights of home and looking outward, far beyond the path of our own comfortable moon. We'll be turning our gaze towards some of the most extraordinary places in our solar neighborhood. These aren't the worlds you read about every day. They are places where the rules of physics seem to have been painted with the most unusual colors. Worlds of ice that burn and volcanoes that stream, not lava, but water. It's a gentle look at the sheer, sometimes baffling, creativity of the cosmos, reminding us that even the most distant, frozen edges hold their own quiet, captivating secrets. If this soft exploration helps your mind settle or your curiosity find a peaceful home, consider leaving a quiet like and a gentle subscribe. It's the simplest way for others to discover this calm, one sleepy moment at a time. For now, let your thoughts grow light, like dust motes floating in a sunbeam. There is no rush here. The extraordinary worlds are waiting, and we'll begin our journey when you're ready. If you could let your thoughts drift inward from the calm of your room tonight, past the moon and the familiar paths of our satellites, they would eventually settle on a small, quick world tucked close to the Sunday. That world is Mercury. In distance, it is not the farthest of our neighbors, yet it has always been strangely difficult to know, like someone who stands just inside the glare of a bright light, always a little hard to see. From Earth, Mercury never climbs very high in the sky. Because it orbits so close to the Sun, you can only glimpse it near the horizon, in the pale blue just before sunrise, or in the fading colors right after sunset. For most of the day, it is hidden in the sun's brilliance. Long ago, when people watched the heavens with nothing but their eyes, this wandering point of light was so elusive that many thought they were seeing two different objects, one that appeared in the morning and another in the evening. It took patient watching to realize that both belonged to the same small planet, hurrying around the sun on a tight inner track. Even with telescopes, Mercury remained shy. The sun's glare washed out details, leaving only a flickering disk that refused to give up its secrets. Only when our instruments improved, and finally when we sent spacecraft to meet it face to face, did Mercury begin to step out of the light and show the shape of its world. What we found is a planet that is small but surprisingly weighty. Mercury is the smallest of the 8 major planets, with a radius of about 2,440 kilometers, only a bit more than a third of Earth's. If you could place the two side by side in your mind, Mercury would look like a compact metal marble beside Earth's broader globe. It is almost perfectly round, with hardly any difference between its polar and equatorial dimensions, as if it had been quietly polished by time. Yet, for such a small planet, Mercury is remarkably dense. It is heavier than some of the larger moons in the solar system, and its mass reveals an interior dominated by metal. Beneath the surface lies an enormous, iron-rich core that fills more than half of the planet's volume. Around this oversized heart is only a relatively thin layer of rocky mantle, and above that, a stiff crust that may be just a few tens of kilometers thick. Most planets have a balance of rock and metal. Mercury is like a core with only a delicate shell. That shell, the surface we can see, is ancient and scarred. When spacecraft first photographed it in detail, Mercury looked in some ways like our moon, a world covered with craters of every size. These bowl-shaped marks are the remains of countless impacts from asteroids and comets, most of them long ago, when the young solar system was crowded with debris. Careful study suggests that Mercury has not been strongly geologically active for billions of years. Unlike Earth, where continents drift, volcanoes rise, and oceans open and close, Mercury's surface has been comparatively still for a very long time. Its history is written in craters, ridges, and plains that have changed only slowly under the steady touch of time. For many years, that distant, cratered face was all we could glimpse from Earth. Observing Mercury through a telescope meant always fighting the bright background of the Sunday. Then, in the mid-1970 seconds, we reached out more directly. The spacecraft Mariner 10 flew past Mercury 3 times, skimming through the space around it. During those brief visits, it photographed about 45% of the surface and measured the planet's magnetic field and temperature. It discovered that Mercury, despite its small size, has a global magnetic field, hinting that its large metal core is still partially molten and slowly turning. It also confirmed that Mercury's atmosphere is not really an atmosphere at all in the way we experience one, but a thin exosphere, a whisper of atoms, mostly light gases like helium and traces of others, always being stripped away by sunlight and replenished at the same time. After Mariner 10, Mercury slipped back into relative quiet, circling the Sun as it always had. Then, in 2004, the spacecraft Messenger left Earth on a long, winding journey. To reach a world so close to the Sun, it could not simply fall inward. It had to trade energy with several planets along the way, looping past Earth and Venus, slowly reshaping its path until, at last, Mercury could capture it. In 2011, Messenger entered orbit around the small planet and stayed there for 4 years, circling again and again, looking and listening. From that close vantage point, Messenger mapped almost the entire surface of Mercury in fine detail. It traced subtle color changes that revealed different kinds of rock. It measured the planet's gravity and magnetic field and watched how the solar wind bumped and flowed around Mercury's magnetosphere. It revealed strange landforms that seem unique in the solar system, as though this small world had quietly invented a few geological tricks of its own. As Mercury moves along its path, it follows an elongated orbit that takes just 88 Earth days to complete. It is never far from the Sun, but its distance changes enough that the amount of sunlight it receives rises and falls over the course of a year. The way Mercury spins adds another layer of strangeness. It turns on its axis 3 times for every 2 orbits around the Sunday. One full rotation takes about 59 Earth days, so a day on Mercury, measured from one noon to the next, lasts 2 Mercurian years. This special rhythm means that certain places on the surface are heated again and again when Mercury is closest to the Sunday. Over very long times, these regions receive the most intense, repeated blasts of sunlight and are known as hot longitudes or hot meridians. One of the most remarkable places in one of these hot regions is an enormous impact basin called Caloris Planitia, the Plain of Heat. It is one of the largest impact structures in the solar system, about 1,550 kilometers across, taking up roughly 2% of Mercury's entire surface. When the Sun stands high over this area, at the right point in Mercury's orbit, the ground can reach temperatures of about 700 Kelvin, or more than 400 degrees Celsius, hot enough to soften some metals. Caloris formed very early in Mercury's history, nearly 3.9 billion years ago, when a huge asteroid smashed into the still young planet. At the time, Mercury's crust had only recently solidified. The impact would have blown out a deep basin and shattered a vast area of the surface. For a while, that part of the planet may have been a churning, molten sea. Lava from the interior welled up, flowed across the basin floor, and slowly cooled into the smoother plains we see today. Around the rim, the collision raised a ring of broken mountains and hills, encircling the basin like a jagged crown. From orbit, Caloris appears as a bright patch, a pale oval surrounded by darker, older terrain, a scar still glowing faintly in comparison to the rest of the surface. The floor of Caloris is not flat and featureless. It is dotted with craters and crossed by gentle ridges. Within it lies one of Mercury's most unusual structures, a pattern of long, narrow troughs radiating from a central region called Pantheon Fossae. Imagine hundreds of shallow, elongated depressions, stretching outward like spokes from a hub. Most are only a few kilometers wide, but can run for over 100 kilometers. Near their center sits a crater named Apollodorus, somewhat offset from the exact middle. From above, the whole formation looks like a delicate starburst of fractures carved into stone. No one is yet completely certain how Pantheon Fossae formed. One idea is that the crust in this region was pulled and pushed by forces deep below, perhaps as the basin floor slowly sank or flexed over time, creating cracks that opened outward from a stressed center. Another idea is that as Mercury's interior cooled, it shrank slightly, and the stress of that contraction fractured the surface in complex ways. The Apollodorus crater may have played a role, or it may have arrived later, superimposed on an older pattern. Whatever the details, this radial network appears to be unique. No other planet or moon we have studied so far has quite the same kind of stone sunburst. If Caloris is a place of intense light and heat, Mercury's polar regions tell the opposite story, one of deep, persistent cold. Mercury's axis is tilted only a tiny amount, so at its poles, the sun never rises high in the sky. In some deep craters, the walls are tall enough that sunlight never reaches the floor at all. These permanently shadowed regions are like pockets of eternal dusk, where the ground has not seen direct sunshine for millions, perhaps billions, of years. Around Mercury's north pole lies a broad, cratered plain called Borealis Planitia. In the deepest, shadowed interiors of some craters there, temperatures can drop to about 80 Kelvin, far below anything you would normally find on Earth's surface. In these cold traps, Messenger's instruments detected bright radar reflections that match what we would expect from water ice. It seems that, hidden beneath a thin blanket of dark, dusty material, there are patches of frozen water up to a couple of meters thick. The dust covering acts as insulation, helping protect the ice from small amounts of scattered light and from the slow heating that might otherwise cause it to disappear. Nearby, on sunlit crater rims and slopes, the temperature can climb much higher, yet Mercury's exosphere is so thin that it cannot carry heat efficiently from place to place. There are no winds to blend the warmth of one region with the cold of another. As a result, you can have extreme contrasts over short distances. One patch of ground in perpetual darkness at bitterly low temperatures, and just over a ridge, another that bakes in direct sunlight. Each small area keeps its own climate, almost entirely isolated from its neighbors. Moving away from the pole toward lower latitudes, the surface remains heavily cratered, but new features emerge. Near the same latitude as Caloris Planitia, but thousands of kilometers to the west, lies another large impact basin called Rachmaninoff. Its diameter is nearly 290 kilometers, and unlike many of Mercury's oldest craters, it appears relatively young, likely about 1 billion years old. At its center rises a ring of mountains, a peak ring, formed when the crust rebounded from the force of the impact and then collapsed into a circular ridge. Within this central ring, the rocks look subtly different. They show colors and textures that suggest they were once molten lava, later cooled and solidified. Rachmaninoff is thought to be one of the last places on Mercury where volcanic activity reshaped the surface, a final episode of internal warmth spilling out before the planet grew mostly quiet. Inside this basin, scientists have identified the lowest point on Mercury's surface, a depression about 5.3 kilometers below the planet's average level, a low spot at the bottom of an already deep bowl. Beyond Rachmaninoff's ring, smoother, darker plains stretch outward like a cooled sea of ancient lava. Crossing parts of these plains and many other regions of Mercury are long, steep cliffs called lobate scarps, where one piece of the crust has been pushed up over another. Among them, one stands out: Enterprise Rupes, the largest known scarp on the planet. It runs for more than 800 kilometers, and in some places, it rises several kilometers high, forming a giant, broken step in the landscape. These scarps are thought to be the result of Mercury's slow cooling over billions of years. As its enormous core lost heat, it contracted slightly. The outer rocky layers had to adjust to this shrinking interior. Because the solid crust could not compress smoothly, it crumpled and broke. One block of crust was thrust up and over another, creating long cliffs that cut across craters and plains alike. From measurements of these structures, scientists estimate that Mercury may have shrunk by about 1% in volume as it cooled. Enterprise Rupes is one of the largest visible wrinkles from that gradual contraction. Part of this great scarp lies within another huge impact basin, Rembrandt, which is about 700 kilometers across. Inside Rembrandt, the surface is a tapestry of ridges and fractures. Narrow mountain ridges run from near the rim toward the center. Another ridge forms a large partial ring on the basin floor. There is also a pattern of intersecting troughs and cracks, like a spiderweb etched into the ground. By studying these overlapping features, scientists can tease out the sequence of events: the impact that formed the basin, the flooding of lava that smoothed parts of it, and the later stresses from the planet's cooling and shrinking that folded and broke the surface again. Even with so much careful observation from Earth, from Mariner 10, from Messenger, Mercury still holds many unanswered questions. Its massive metallic core, its unusual spin-orbit rhythm, the mixture of extreme heat and sheltered ice, the timing and extent of its volcanism, and the details of its magnetic field all invite deeper understanding. For a tiny world, it seems to carry a surprisingly rich and complicated story. That is why another traveler, Bepi Colombo, is on its way. This mission, a partnership between European and Japanese space agencies, is following its own intricate path inward, using repeated flybys of planets to slowly reshape its orbit until Mercury can capture it. Once in orbit, Bepi Colombo will carry a suite of instruments to examine Mercury's surface in more detail, to measure the composition of its rocks and polar ices, to study its exosphere, and to watch how the solar wind flows around its magnetosphere. Each new piece of data will help fill in the gaps, smoothing the rough edges of what we know. For now, as you breathe and rest here on Earth, Mercury continues its swift journey around the Sun, turning 3 times for every 2 circuits, showing one cratered face and then the other to the light. It is a world of contrasts, small yet dense, ancient yet still holding traces of long-ago fire, close to the sun yet harboring ice in permanent darkness. You may never see it clearly with your own eyes, but it is there, keeping its own quiet time, a small metal-hearted planet whispering its story across the inner solar system while you drift gently towards sleep. And if, in your thoughts, you let that whisper fade into the background glow of starlight and then slowly glide outward from Mercury's orbit, a little farther from the sun, another bright world comes into view. This is Venus, often the first star you notice in the soft light of evening or before dawn. It hangs low above the horizon, steady and pale, like a quiet lantern at the edge of night. Behind that gentle appearance is a planet moving on a tight inner track. Venus circles the Sun at about 72% of Earth's distance and completes one orbit in roughly 225 Earth days. As Earth and Venus move at different speeds, a rhythm appears. About every 584 days, the two worlds draw especially close. During these meetings, Venus tends to present nearly the same face toward Earth again and again, as though it were slowly turning the same cheek to us. Some scientists think Earth's distant pole may have nudged Venus into this pattern over long ages. Others suspect it may just be an accident of timing. In many ways, Venus looks like Earth's sibling. Its radius is about 95% of Earth's, and its mass a little more than 4/5 as large. If you could hold the two worlds in your imagination, side by side in the dark, they would feel almost like twins in size and weight. From those simple numbers alone, you might picture Venus as a slightly warmer version of home, a rocky world with familiar mountains and perhaps a brighter sky. But the way Venus spins and the way it hides itself tells a very different story. The planet rotates extremely slowly, taking about 243 of our days to complete a single turn, and it spins backward compared with most other planets. If you floated above the clouds and watched the ground below, you would see it creeping from east to west instead of west to east. Its axis is tilted only a few degrees, so there are almost no seasons. A day on Venus lasts longer than its year, and from the surface, the sun would appear to drift slowly in the wrong direction across a sky that never clears. For a long time, almost everything beneath those clouds was hidden. Venus is wrapped in a thick, reflective atmosphere that bounces sunlight back into space. Through telescopes, we see only a smooth, bright disk, with no hint of what lies below. Under that veil, people once imagined steaming jungles, shallow oceans, or even complex life. The real surface began to emerge when we learned to look with radio waves instead of visible light. Certain radio frequencies can slip through the clouds, bounce off the solid ground, and return. By sending out these signals and listening for their echoes, we can build a radar portrait of the land below. In the late 1970 seconds, the Pioneer Venus orbiter and Soviet spacecraft used this method to sketch the first global maps. They were rough, showing only the largest shapes, but enough to reveal that Venus has highlands, lowlands, and Great Plains. In 1990, the Magellan spacecraft arrived to sharpen the picture. For 4 years, it orbited Venus, sweeping its radar beams across the hidden face. By the time its work was done, it had mapped about 95% of the surface in much finer detail, revealing structures down to the scale of hills and valleys. Even today, Magellan's data are our clearest window onto Venus's terrain. From those maps, and from what we know about rocky planets, scientists sketch a picture of Venus's interior. At its center is thought to be a dense metallic core, likely rich in iron, making up roughly a quarter of the planet's mass. Around it lies a thick mantle of hot rock, and above that, a relatively thin crust. Unlike Earth, Venus seems to have no strong global magnetic field, which suggests that its core is not vigorously churning. The outer shell of Venus also behaves differently from Earth's. Our planet's crust is broken into plates that slowly drift and collide, reshaping continents and ocean floors. On Venus, the lithosphere, the stiff outer layer, seems more like a single shell that bends, buckles, and cracks in patches rather than sliding in great pieces. High temperatures and the way rocks deform under pressure may keep large plates from forming. The result is a style of geologic activity that belongs to Venus alone. One of the first things you notice in the radar images is that Venus has fewer large impact craters than some other rocky worlds. That suggests much of the surface is relatively young. Wide areas are covered by dark basalt plains, lava that once flowed across the ground and cooled. At some point in the past, and possibly more than once, volcanoes and long fissures may have poured out enough molten rock to resurface large regions, burying older scars. Within and around these plains are landforms that do not have close twins elsewhere. Tesserae are one example, complex, rugged highlands where the ground is folded and broken into intersecting ridges and grooves. In radar images, they look like tightly crumpled fabric pressed flat again, still holding its wrinkles. Other distinctive features include arachnoids and coronae, large, roughly circular or oval structures, often hundreds of kilometers across, ringed by fractures and ridges. Instead of being carved by incoming asteroids, they seem to rise from forces below, hot rock slowly pushing upward, or blocks of crust sinking and dragging the surface with them, leaving patterns that resemble spider webs or halos cut into stone. On a map colored by height, one broad, bright shape near the equator stands out immediately. This is Aphrodite Terra, the largest highland region on Venus. In the same way we speak of continents on Earth, places like Aphrodite Terra and its northern cousin Ishtar Terra can be thought of as Venusian continents. Aphrodite stretches for many thousands of kilometers along the equator, with a width of several thousand more. Its total area is comparable to that of Asia. Within Aphrodite, Terra lies Atla Regio, home to some of the planet's tallest volcanoes. Among them is Ma'at Mons, a broad shield volcano whose summit stands several kilometers above its surroundings and roughly 8 or 9 kilometers above the planet's average radius. Its flanks are draped in smooth-looking lava flows with few impact craters. That lack of scars suggests that at least some of its lava may have erupted comparatively recently in geological terms. If Venus still has active volcanism today, places like this are among the most likely to be alive. Farther west, Aphrodite becomes a maze of ridges and faults. Mountain chains run in different directions, as if several slow forces have pressed and pulled the crust over long spans of time. Deep fractures slice through the highlands, some filled with solidified lava. The surface there seems to tell of crust being squeezed, torn, and then patched again and again. South of these highlands lies a vast region called Guinevere Planitia. Despite its name, it is not a simple flat plain. It stretches across a huge area and contains a mix of folded terrain and smoother lava fields. Tectonic forces may have crumpled the crust here into ridges and gentle swells, while lava pouring from fissures spread outward to fill low spots. The result is a patchwork of wide flats, bordered by more rugged uplands. On the western edge of Guinevere, Planitia rises Beta Regio, a roughly circular upland that appears bright in radar images, and was one of the first Venusian features to receive a name. It is about 2,000 kilometers across and hosts large volcanic structures. Somewhere in this region lie the resting places of some of the earliest Venus landers, Soviet Venera spacecraft, that fell through the thick atmosphere in the 1,970 seconds. They survived on the surface for less than an hour, but in that brief time, they sent back the first close images and direct measurements. The rocks they sampled turned out to be basaltic, similar to volcanic rocks on Earth, confirming that much of Venus's surface is built from solidified lava. If you let your attention drift northward from the equator, you reach Ishtar Terra, the second great highland, nearer the North Pole. It stretches several thousand kilometers east to west and a couple of thousand north to south, giving it an area only slightly larger than Australia. In its center rises the tallest mountain range on Venus, Maxwell Montes. Maxwell Montes towers about 11 kilometers above the planet's average surface level and roughly 7 kilometers above the surrounding plains. Its summit is not a sharp point but a broad plateau a few hundred kilometers across. Although cool is a strange word to use for a place that still bakes at around 380 degrees Celsius, Maxwell Montes is indeed cooler than the lowlands, where temperatures hover near 460 degrees. The air at its heights is somewhat thinner too, with pressures about half those at the surface, though still tens of times denser than Earth's sea-level atmosphere. In radar images, these mountaintops glow with unusual brightness. One idea is that, at these slightly lower temperatures, certain metal-rich compounds in the atmosphere can condense onto the rocks, forming a thin, shiny coating. Instead of water snow, Venus may have a kind of metallic frost dusting its highest peaks. All of this intricate geology is wrapped in an atmosphere that is as harsh as it is beautiful from afar. Near the surface, the pressure is about 90 times that at Earth's sea level, comparable to what you would feel deep beneath an ocean here. The temperature is around 737 Kelvin, roughly 460 degrees Celsius. The air is mostly carbon dioxide, with clouds of sulfuric acid droplets swirling in thick layers overhead. Under such conditions, ordinary metals soften, many familiar materials fail, and even specially designed electronics struggle to survive. Robotic landers sent to the surface have faced this environment with as much protection as we can give them, yet they have endured only short periods, often less than an hour before the heat and pressure overwhelmed them. In that brief time, they have sent back images of flat, fractured rocks and dusty plains under a heavy, yellowish glow. Each landing reminds us how close Venus is in space and how distant it remains in terms of comfort. Because of these extremes, the idea of transforming Venus into a world comfortable for humans seems, at least for now, beyond reach. Thinning its atmosphere, cooling its surface, and changing its chemistry would require changes on a scale we can hardly imagine. Venus, as it is not a world we can easily reshape. Higher up in the atmosphere, however, there are gentler layers. At altitudes where the tops of the cloud decks float, the pressure and temperature come surprisingly close to those at Earth's surface. The air there is still toxic and filled with acid droplets, but it is no longer crushingly dense, and the heat is far more bearable. Some scientists and dreamers have suggested that human habitats might one day drift in these layers, carried by large balloons or aerostats, floating above the deadly surface in an ocean of cloud. From your quiet place on Earth, Venus remains a bright point at dawn or dusk, serene and distant, its storms and lava fields hidden behind a glowing veil. It is nearly Earth's twin in size, but utterly different in mood. A world of crushing pressure, searing heat, volcanic plains, folded highlands, and metallic snow. Somewhere beneath its endless clouds, mountains and plains wait in their furnace air, keeping their own slow time. As you breathe under our thinner, kinder sky, that neighboring planet continues to turn, its secrets still half heard, waiting patiently for the day when we learn how to visit and listen more closely. And if, in that same quiet, you let your thoughts slip past those glowing clouds and keep drifting outward from the sun, the next world slowly comes into view. The bright lantern of Venus falls behind you, and ahead, a smaller, colder globe appears against the dark. This is Mars. Today it looks dry and quiet, but if you could roll time back by billions of years, the planet in front of you would feel very different. Back then, Mars is thought to have worn a thicker cloak of carbon dioxide, holding in heat the way a blanket holds warmth around a sleeping body. Under that dense atmosphere, liquid water could last on the surface. Rivers once traced long paths across the land, carving valleys and branching like the lines in a palm. Much of the northern hemisphere may have been covered by a broad ocean, a cold, shallow sea reflecting a soft, pinkish sky. All of that is gone now. What remains are only the traces: dried riverbeds, rounded channels, shorelines cut into old rock. The story most scientists tell is that Mars simply could not protect its early air for long enough. Its magnetic field, if it had one, was weak and unstable. Without a strong, steady shield, the planet was left exposed to the solar wind, a constant flow of energetic particles from the sunday. Over hundreds of millions of years, those particles chipped away at the upper atmosphere. Water vapor high above the ground was broken into hydrogen and oxygen by sunlight. The light hydrogen drifted upward and escaped into space. The heavier oxygen stayed behind and slowly reacted with the rocks at the surface. Iron in those rocks turned to iron oxides, rust tinting the dust and sand. Layer by layer, the planet's face changed color until it became the reddish world we know, coated in a thin orange film of powder that can be lifted into the air by the gentlest of winds. That thin dust and ground that stays frozen for most of the year are what's left of the once abundant water on Mars. Ice still lies buried under the surface and at the poles, and small amounts of vapor linger in the air. But the great seas and flowing rivers belong to a different age. To understand how Mars arrived at this quieter state, it helps to look beneath its surface, into the layers hidden from view. A recent lander, named InSight, listened to Mars for several years with a sensitive seismometer, measuring tiny tremors and quakes. From the way those vibrations traveled through the planet, scientists have pieced together a picture of Mars's interior. At the center lies a large, hot core, rich in iron with traces of sulfur and nickel. Its radius is more than half that of the entire planet, a dense heart that takes up a surprisingly large portion of the interior. Temperatures there reach thousands of degrees, but for reasons still being studied, the core does not generate a strong, global magnetic field today. Perhaps its motions are too gentle, or its structure is too settled to stir the kind of powerful flows that protect Earth. Around this core is a thick mantle of rock, some of it partly molten, extending for well over 1,000 kilometers. Deeper parts of the mantle hold heavier oxides. Higher up, the rock is richer in minerals like olivine and other silicates, similar to what we find in Earth's upper mantle. Wrapping around it all is the crust, the outermost solid shell. On Mars, This crust averages about 50 kilometers in thickness, much thicker than Earth's ocean floors, and closer to the thickness of our continents. The crust itself is not the same everywhere. In the northern hemisphere, it seems to be dominated by lighter, more evolved volcanic rocks, while the southern highlands are older and built mostly from darker basalt. This difference hints that the two hemispheres formed in different episodes or under different conditions, like two chapters in the planet's early life written in different inks. For decades, orbiters circling Mars have been taking pictures of its surface, patiently building up a detailed global map. Some features are small and subtle, visible only when you zoom in. Others are so vast that they can be seen even with telescopes on Earth. One of the most striking of all is a long, jagged scar near the equator, Valles Marineris. Valles Marineris is a system of enormous canyons and chasms stretching for about 4,500 kilometers a distance that would span the continental United States. In places, the canyons are hundreds of kilometers wide and several kilometers deep, a gash across the surface that makes Earth's Grand Canyon look like a narrow scratch by comparison. At its western end, the system runs into a huge volcanic uplift known as the Tharsis region, a swelling in the crust that hosts some of the tallest volcanoes in the solar system. Near the edge of this plateau, almost in its center, lies a place with a name as soft as a whispered spell: Noctis Labyrinthus, the Labyrinth of Night. Noctis Labyrinthus is a region of chaotic terrain, an intricate tangle of deep, steep-walled troughs and broken blocks that stretches for more than 1,000 kilometers. From above, it looks as though the ground has cracked, dropped, and shattered into irregular pieces, leaving long, shadowed cuts that intersect and branch. The tops of the blocks are capped with softer, lighter material, worn down over long ages, while the underlying bedrock at their base is harder and more resistant. Over billions of years, the edges of these chasms have collapsed again and again, sending landslides pouring down the slopes. In some places, the scars of these collapses are still visible as slumped, layered fans of rock and dust. Many scientists think that long ago, rain or snow fell on the highlands around Noctis Labyrinthus and gathered in these depressions, flowing eastward as powerful streams. The floors of the chasms bear the marks of deep erosion, and the layers exposed in their walls suggest that sediments were laid down, reworked, and laid down again by water. Spectral studies, ways of analyzing the light reflected from the surface, show that Noctis Labyrinthus is rich in minerals that almost certainly required liquid water to form: hematite, some forms of opal, various sulfates. Their presence is like a quiet signature, confirming that water once moved slowly through the rocks here, dissolving, carrying, and reshaping. Even today, this region appears to be one of the more humid places on Mars. Orbiters have watched fog gather in the chasms and valleys, especially during the colder hours. The idea is that water trapped in the soil can slowly evaporate into the thin Martian air during the day. The high canyon walls then act like barriers, keeping this slightly moister air from spreading out. As night falls and temperatures drop, the water vapor condenses into tiny ice crystals, forming clouds and, eventually, a fragile frost that settles along the ground and walls, a faint, nightly echo of long-vanished rivers. If you follow the maze eastward, the tightly packed canyons of Noctis Labyrinthus gradually open into the main body of Valles Marineris, where gigantic troughs run side by side and occasionally intersect. Over time, vast amounts of water, when Mars was young and wetter, seemed to have cut deep paths through the rock, and later, winds and dust storms widened and softened the edges, eating away at sharp faces and sculpting terraces as the planet's climate dried. No matter which branch of this canyon system you follow, many paths eventually lead to a particularly deep and dramatic section called Coprates Chasma. Here, the canyon floor lies about 11 kilometers below the surrounding plateau, a depth that is hard to feel until you imagine standing on the top of the cliffs, looking down into an atmosphere that thins with every meter. Calculations suggest that in ancient times, Coprates Chasma may have held a long, narrow lake stretched out along the canyon floor. At its fullest, its volume might have been comparable to that of the Black Sea on Earth. If that lake existed, its sediments could be a treasure trove, layer upon layer of mud and minerals quietly deposited over ages, possibly preserving signs of simple life if it ever took hold on Mars. The slopes of Coprates Chasma, with their exposed bands of rock, are like the pages of a geological book left open. Each layer tells of a different time: volcanic eruptions, floods, quieter periods of dust and ash settling out of the air. For future missions, this region is one of the most enticing targets. A rover or lander there could read those pages close up, searching for patterns and clues that are invisible from orbit. As you drift farther east along Valles Marineris, the walls gradually lower, the canyon widens, and the whole system slowly merges with a broad, low-lying region. Here, the traces of flowing water soften into rounded terraces and elongated islands of higher ground, shapes that look comfortingly familiar if you've ever seen satellite images of river deltas on Earth. In places like the Amazon Delta or the Nile's broad fan of channels, sediment carried by rivers and spread by currents builds up in gentle steps and lobes. Mars shows similar forms here, as if the planet once had its own river mouths and spreading wetlands, now long dried. Taken together, Valles Marineris and its connected basins are among the clearest, grandest pieces of evidence that water once played a central role in shaping the Martian landscape. They are a reminder that the small, cold world we see now had a more active, wetter youth. And yet, for all our close-up images and careful maps, these immense canyons remain untouched by wheels and footprints. Every rover so far has explored gentler terrain, craters, plains, and small valleys more suited to safe landings. Valles Marineris has only been explored from afar by machines looking down from orbit, tracing its shadows and measuring its depths with the patience of years. Some quiet evening in the distant future, a different story may unfold. A human lander easing toward the edge of those cliffs, or a small machine descending carefully into their sheltering depths. For now, though, the great rift of Mars lies in silence, keeping its records in stone and dust, while you lie here, under Earth's softer sky, listening to the faint echo of its ancient waters in the dark. If, in your thoughts, you gently rise away from those shadowed canyons and drift eastward over the red deserts, the view changes. The deep scars of Valles Marineris fall behind, and beneath you the landscape stretches into a long expanse of bare rock and dust. After crossing thousands of kilometers of cold, empty plains, a broad circular scar comes into view: Gale Crater. About 3.8 billion years ago, a massive asteroid struck Mars here, carving out a depression roughly 150 kilometers across. The impact shattered rock, melted crust, and left behind a deep basin with raised rims. Over time, sediments began to collect inside, layer after layer settled out dust, sand, mud, perhaps ash from distant volcanoes building up a mound near the center. Today, that mound is known as Mount Sharp, a tall, irregular upland made of finely stacked layers like the pages of an ancient book, each one keeping a record of a slightly different Mars. In the distant past, Gale may have held a lake. In that picture, water pooled inside the basin, perhaps filling much of the crater and lapping against its inner walls. Mount Sharp might have been a central island, surrounded by shallow water, later revealed as the lake dried and the wind slowly stripped material away. Whatever its exact history, Gale Crater is a place where water, wind, and time have worked together for billions of years, building and carving, erasing and revealing. In recent years, this quiet basin became home to a visitor from Earth. On the 6th of August 2012, a complex robot the size of a small car lowered itself gently onto the crater floor. Its name was Curiosity. Built to be both a rover and a mobile laboratory, it carried cameras, drills, ovens, and instruments designed to sniff the air and taste the rocks. Its mission was simple to say, but hard to carry out: to find out whether Mars had once offered conditions suitable for life, and to understand more deeply the climate and geology of this red world. Almost as soon as Curiosity began to move, the ground around Gale started sharing its secrets. Early images showed rounded pebbles and a shallow channel cut into the landscape, a dried stream bed shaped by running water. The site was named Peace Vallis, the Valley of Peace, and it was one of the clearest signs that liquid water once flowed here with enough strength to carry stones, polish them, and lay them down in beds. From its landing site, Curiosity rolled eastward and reached a patch of wind-blown sand and small drifts, nicknamed Rock Nest. There it scooped its first samples of Martian soil and fed them into its tiny onboard laboratory. The instruments found that even this dry, dusty ground contained a small but real amount of water locked in its grains, roughly a few percent by weight. In that thin desert sand, there was still a trace of the old, wetter Mars. Curiosity then turned and made its way toward a region called Glenelg, where 3 different types of terrain meet. There, more ancient rocks waited, hardened mudstones and layered sediments shaped when water still moved over and through the ground. Farther along its path, the rover crossed the dark ripples of the Bagnol Dunes, low hills of sand that creep and shift under the push of the thin Martian wind. These dunes are younger features in geological terms, a reminder that even now, Mars is not entirely still. Its surface is slowly rearranged by dust storms and breezes that stride across the plains. From the dunes, Curiosity began a long, careful climb up the lower slopes of Mount Sharp, passing into a ridge called Vera Rubin. The ground beneath its wheels started to change. Instruments detected hematite, an iron oxide that, on Earth, often forms in the presence of liquid water. Much of the ridge turned out to be rich in this mineral. That suggested that the rocks here had once interacted with water over extended periods, perhaps in lakes or groundwater systems. Each drill hole, each powdered sample, added another quiet line to the story. This place had not always been so dry. Curiosity was originally designed for a mission of about 2 Earth years. Instead, it has remained awake and working on Mars for more than 3,000 Martian days, or sols many times its planned lifetime. Over that time, it has traveled nearly 30 kilometers across rough terrain, climbing over rocks, skirting sand traps, and pausing often to examine promising outcrops. It has collected dozens of samples, drilled into stones, sifted soil, and heated it in tiny ovens to release gases for analysis. Among the chemicals detected were not only signs of water and minerals, but also organic molecules, carbon-bearing compounds, such as simple aromatics, and others that, on Earth, can be linked to life or to non-living processes in the crust. These molecules are not proof of Martian organisms, but they show that the building blocks of life can survive in the rocks, even after long exposure to radiation and time. Through it all, Curiosity's cameras have sent back thousands upon thousands of images: dusty horizons under pale pink skies, close-ups of layered stones, views of distant hills softened by the haze. Leaving the rover to continue its slow climb, you can let your attention drift south and east, across more craters and plains, until another enormous scar appears, Hellas Planitia. From orbit, this feature is striking a vast, circular basin, more than 2,000 kilometers across and over 7 kilometers deep. It is one of the largest impact structures in the solar system. Hellas likely formed around 4 billion years ago when a huge asteroid, perhaps 100 kilometers in diameter, struck Mars at high speed. The impact released energy beyond our usual forms of comparison. Rock was vaporized, melted, and blasted outwards. Billions of tons of material were hurled far from the site, some falling back to Mars, many hundreds or thousands of kilometers away, some possibly driven all the way into space. In the aftermath, a deep cavity remained. At that time, Mars is thought to have been warmer and wetter than it is now. The low-lying basin of Hellas may have collected water quickly, forming a large lake or even a sea without an outlet, a place where rivers ended and sediments slowly settled to the bottom. Over immense spans of time, as the climate changed and water retreated, that basin dried and froze, leaving behind the Hellas we see today. From a distance, the floor of Hellas might look smooth and flat, a pale, gently curved bowl. Up close, it is far more intricate. The terrain is broken by low hills, ridges, and shallow fractures. Many of these features seem to be shaped by the behavior of ice within the subsurface. In permafrost regions on Earth, places like the Arctic tundra, similar patterns arise as buried ice slowly shifts, melts, and refreezes, pushing and pulling the ground above it into hummocks and polygonal cracks. On Mars, something like that appears to be happening in parts of Hellas, hinting at thick layers of frozen water hidden just below the dust. Because Hellas is so deep, the air at its bottom is denser than in most other Martian lowlands, perhaps about twice the average surface pressure. That extra weight of atmosphere, though still thin compared to Earth, allows weather here that is unusual for Mars. Observers have seen hazy mists forming over the basin, pooling in the low areas like ghostly fog. Winds sweep some of that haze up and over the crater rim, but the fine droplets and ice crystals soon dissipate in the thinner air beyond or settle back onto the frozen ground. In winter, frost can cover much of Hellas Planitia. When Mars is farther from the sun and the temperatures drop, carbon dioxide from the atmosphere condenses onto the surface as a bright, seasonal coating. From Earth, this frosty basin can appear as a large, pale patch on the disk of Mars, and for many years, it was mistaken for a high, reflective plateau. Only detailed mapping showed that it was, in fact, one of the deepest hollows on the planet. From Hellas, if you turn and travel northward, you eventually reach a smaller but very special crater, Jezero. Long ago, Jezero held a lake. 2 ancient river systems, now dry, once flowed into it, one from the north, one from the west, bringing water and sediments from distant highlands. The traces of these rivers are still visible today as winding channels and fan-shaped deposits, the frozen remains of deltas that once spread out where flowing water slowed and dropped its load of sand and silt. Because lake beds and deltas on Earth are good places to preserve signs of past life, Jezero Crater became a prime target for a new rover mission. On the 18th of February 2021, a rover named Perseverance descended into Jezero, riding a complex landing system that lowered it gently to the surface. The original plan was for the rover to set down near a region called Three Forks in the ancient river valley. But the real atmosphere, with its unpredictable winds and density variations, nudged the spacecraft slightly off course. Perseverance touched down about 1.7 kilometers southeast of the intended spot, separated from the heart of the delta by a broad stretch of broken, sandy terrain known as Saita. That rough ground, with its ripples and hidden rocks, would have been dangerous to cross blindly. Here, a small companion came into its own. Attached to Perseverance was a tiny helicopter, Ingenuity, a slender craft with counter-rotating blades, built to test whether powered flight was possible in the thin Martian air. Once deployed, it rose a few meters above the ground, hovered, and then began to make short scouting trips, capturing wide-angle images of the surrounding landscape. From its aerial vantage point, Ingenuity looked out over the delta and took detailed pictures of features like Kodiak, a small plateau with clear layers of sediment, about 2 kilometers from the rover's landing site. Those views helped the science team choose paths and targets, highlighting places where ancient lake deposits might be best preserved. On the ground, Perseverance started its own slow journey. At first, it traveled south along the edge of Saita, collecting samples from the crater floor and examining rocks that record some of the earliest history of Jezero. Ingenuity flew ahead or alongside, flight after flight, proving that a delicate machine could navigate and land safely in the rarefied Martian atmosphere. Later, the rover tried to take a more direct route toward the delta, turning west and attempting to skirt around the southern tip of Saita and then up along the crater's interior. But the terrain there proved more difficult than hoped, rocky, uneven, and potentially hazardous to the rover's wheels and drive system. After careful consideration, the team commanded Perseverance to turn back, retracing part of its path, and then circling around the safer northern side of the sandy region. Step by step, sol by sol, the rover closed in on the delta from a different angle. In April 2022, a little more than 400 Martian days after landing, Perseverance finally arrived at the base of the ancient river deposits. There it began to explore the layered rocks, drill cores, and store samples in tubes that may one day be returned to Earth by a future mission. By now, Perseverance has traveled many kilometers across Jezero's floor and lower delta. It has collected a growing set of rock and soil samples, each carefully documented and sealed. Its instruments have measured the chemistry and textures of the rocks, taken more than 100,000 images, and listened for small quakes that offer clues about the interior structure of Mars. A small experiment called MOXIE, tucked inside the rover, has pulled in Martian air and converted carbon dioxide into oxygen in modest amounts, only tens of grams, but enough to show that such a process could one day help support human explorers or fuel rockets for a return trip home. Ingenuity, expected at first to make only a handful of test flights, has far exceeded its original goals. It has flown dozens of times, covering several kilometers in total, scouting ahead and offering views that rovers on their own could never obtain. Together, rover and helicopter have turned Jezero from a distant crater on a map into a place with familiar landmarks, hills, flats, and sky. Every so often, Perseverance points its cameras upward instead of down, against the dim, salmon-colored Martian sky. Tiny moons move in their own quiet rhythms. In some images, Deimos appears as a small white dot, barely more than a star, drifting slowly above the horizon. In others, Phobos passes in front of the sun, creating a brief, lopsided eclipse. These events are not just beautiful. The precise way the moon's shadow moves lets scientists refine their understanding of Phobos's orbit and of how Mars itself flexes under the pull of its satellite. Unlike Earth, with its single large moon, Mars is accompanied by two small, irregular companions, Phobos and Deimos. They are more like captured stones than round worlds, dark, cratered, shaped like lumpy potatoes rather than spheres. Their surfaces reflect little light, and their spectral signatures resemble those of certain carbon-rich asteroids. That has led some to suspect that they may be remnants of a captured object from the asteroid belt, torn into pieces by Mars's gravity long ago. Another idea is that they formed from debris thrown into orbit when a large protoplanet collided with young Mars, with the fragments later gathering into a few compact clumps. Phobos, the larger of the two, orbits closer in. It circles Mars at an altitude of only a few thousand kilometers above the surface, far nearer than our moon is to Earth. In fact, some man-made satellites around Earth fly higher than Phobos does above Mars. Yet because Phobos is small, only a couple of dozen kilometers across, it still looks modest in the Martian sky, smaller than our moon appears to us. Its low average density hints that it may be a rubble pile, a cluster of rocky fragments held together by gravity, with empty spaces between them. Tidal forces from Mars slowly tug at Phobos's orbit, causing it to spiral inward bit by bit, dropping roughly a couple of meters closer to the planet each century. Far in the future, tens of millions of years from now, it may be pulled apart, forming a temporary ring before its pieces rain down onto Mars's surface. Deimos, the smaller moon, orbits much farther out. Its path carries it tens of thousands of kilometers above the planet, and its distance is slowly increasing. Over very long timescales, it may eventually drift away from Mars entirely, leaving its old partner behind. Deimos is even darker than Phobos, reflecting only a tiny fraction of the sunlight that hits it. Seen from Mars with the naked eye, it would appear as a bright, slow-moving point rather than a resolved disk. From the surface, it can look as though Deimos and Phobos move toward or away from each other in the sky, but that is an illusion created by their different orbits. Both moons travel around Mars in the same general direction, tracing their own quiet loops day after day. While you rest under Earth's broad, blue sky, these small companions continue their endless circuits around a cold, red world. Rovers crawl slowly across dusty craters. A tiny helicopter hums above ancient deltas. Deep basins hold frozen records of vanished lakes. And high overhead, two dark moons drift through a thin atmosphere, casting fleeting shadows on a planet that once knew rivers and seas and may one day hear human footsteps on its rust-colored ground. Far beyond the orbit of Mars, where the sun has shrunk to a bright, distant coin in the sky, another world waits in the glow of a giant planet. More than 400 years ago, in 1610, Galileo lifted a small telescope to his eye and saw, for the first time, 4 tiny points of light close to Jupiter. Night after night, he watched them change position, shifting from one side of the planet to the other. It slowly became clear that these were not stars at all, but moons circling a distant world. Today, we call them the Galilean satellites: Io, Europa, Ganymede, and Callisto. Ganymede would turn out to be the largest moon in the solar system. Europa and Callisto would become quiet favorites in the search for hidden oceans and possible life. Io, the innermost of the 4, would reveal something different, a kind of restlessness so intense that it reshapes its surface again and again, refusing to sit still. For a long time, telescopes on Earth could see Io only as a small, fuzzy disk, tinted in odd shades of yellow and orange. Its true nature was a mystery. The color suggested sulfur and strange chemistry, but details of its surface and interior remained guesses. Only when spacecraft began to fly past Jupiter did Io step into clearer view. We now know that Io is one of the largest moons in the solar system, just a little smaller than our own moon. Its radius is about 1,800 kilometers, and its mass is a bit more than our moon's. That alone would not be so remarkable, but when you compare the two more closely, something stands out. Io is noticeably denser. Its average density is higher than that of almost any other moon we know, closer to compact rock than to a mixture of rock and ice. It is as if someone took a rocky world, squeezed out almost all of the lighter, icy material, and left behind a heavy, tightly packed core. To understand why Io is so dense, you have to imagine peeling it open. At its center lies a metallic heart, rich in iron, with some sulfur mixed in. This core makes up a significant fraction of Io's mass, a compact ball tucked deep inside. Around it lies a thick mantle of rock, dominated by the mineral forsterite, a magnesium-rich silicate that can withstand high temperatures and pressures. Closer to the surface, the conditions change. Models and measurements suggest that the upper part of the mantle is hot enough to be partly molten. There may be an extended layer, a kind of global ocean of magma, tens of kilometers thick, where rock flows slowly like an unimaginably dense, fiery liquid. The temperature there is intense, far hotter than any lava lake on Earth. Deeper down, where the pressure rises, the rock remains solid despite the heat, locked into place. Wrapped around this mantle is Io's lithosphere, a rigid shell of rock perhaps a few tens of kilometers thick. It is not smooth or unbroken. In many places, it is fractured and stretched, forming long depressions and giant pits where molten material can rise and spill out. Unlike many other moons, Io contains virtually no water ice at its surface. Its outer layers are made mostly of basaltic rock and various sulfur compounds. That dryness, combined with its heavy, rock-rich interior, gives Io its unusual density. In the 1,970 seconds, the first close visits by spacecraft transformed Io from a tiny colored disk into a world alive with surprises. The Pioneer probes offered early hints, but it was the Voyager missions that truly changed our picture. When Voyager 1 flew past, the images it sent back stunned scientists. Io's surface was mottled in yellows, whites, and reds, covered with dark spots and ring-like stains. It looked nothing like the battered, cratered faces of many other moons. Instead, it seemed freshly painted, as though someone had smeared bright pigments across it in broad strokes. Then, in some of the images, there was something even more startling. High above the edge of the moon, plumes of gas and dust arched into space, rising hundreds of kilometers above the surface. This was the unmistakable signature of active volcanoes. For the first time, we were seeing eruptions in real time on another world. Jets of material climbing far higher than most volcanic plumes on Earth before falling back in long, delicate arcs. Further observations have revealed that Io has hundreds of active volcanic centers scattered across its globe. If you stood on a safe, imaginary platform and could look with perfect eyes, you would see fountains of lava, glowing lakes, and dark flows spreading over the ground. Per square kilometer, Io is the most volcanically active body in the solar system. The reason lies in its relationship with Jupiter and with its sibling moons. As Io orbits close to the giant planet, Jupiter's immense gravity pulls on it strongly. At the same time, the tugs of Europa and Ganymede keep Io's orbit slightly stretched rather than perfectly circular. As it swings closer and then farther from Jupiter over each orbit, Io is flexed like a soft ball being squeezed and released. That constant kneading generates enormous amounts of heat inside, keeping the mantle partially molten and feeding the volcanoes. Over the decades, many spacecraft, Pioneer, Voyager, Galileo, and others, have imaged Io from different angles and distances. By combining all those pictures, scientists have created detailed geological maps showing plains, mountains, long lava flows, and hundreds of volcanic centers. One of the most striking features on these maps is a huge, roughly circular stain in the southeastern part of the Moon, a broad ring of orange-brown material that spreads over more than 1,000 kilometers. At the center of this ring lies a volcanic complex known as Pele. In visible and infrared images, Pele stands out as one of Io's most powerful and persistent volcanoes. At its heart is a large volcanic depression called a patera, roughly shaped like an irregular, multi-level bowl. Within this cavity, there appears to be a vast lava lake, its surface a shifting patchwork of glowing molten rock and darker cooling crust. The temperature at the hottest spots in this lava can reach well over 1,000 degrees Celsius. The surface is far from calm. Volatile gases dissolved in the magma sulfur compounds, and others struggle to escape as the molten rock rises. When they break free, they drive vigorous upwelling, overturning, and sometimes explosive outbursts. The thin crust that forms on top of the lava lake can crack and founder, sinking back into the melt even as new crust forms elsewhere. Every so often, pressure within this system rises enough that gas and molten fragments burst upward through vents, launching great plumes into space. Some of these plumes reach heights of hundreds of kilometers before curving gracefully under Io's weak gravity and falling back as fine particles. These tiny grains of sulfur and rock settle out onto the cold surface, forming a wide, diffuse ring of deposits around the eruption center. Over time, repeated eruptions from Pele have built up the huge, colorful ring we see today, a volcanic halo large enough to rival an entire country on Earth. Many of Io's volcanoes have their own smaller rings and fans of deposits, but the region around Pele is among the largest and most dramatic. Together, all of this activity creates a thin, patchy atmosphere around the Moon. Io's atmosphere is mostly sulfur dioxide gas, constantly renewed by eruptions and constantly lost to space. Where a plume is rising, the local gas density can be relatively higher. Far from any eruptions, the air thins out to a near vacuum. On the day side, there is just enough gas to form a fragile envelope. On the night side, cooled and condensed, much of it falls back to the surface, leaving the air even more tenuous. Despite how thin it is, this atmosphere interacts with the charged particles trapped in Jupiter's powerful magnetic field. Io races through this environment, and energetic particles slam into its upper gases, causing them to glow. From the right vantage point, you can see faint auroras shimmering above Io's surface, not only near the poles, but also in equatorial regions where incoming particles must pass through thicker parts of the atmosphere. It is a strange echo of the northern and southern lights on Earth, written in different colors over a very different sky. If you leave the lava fields of Pele behind and travel northwest across Io's brightly stained terrain, you eventually come to another kind of wonder. A huge, rugged massif known as Boe Sole Montes. This sprawling mountain complex is hundreds of kilometers wide, a tangle of ridges and cliffs rising abruptly from the plains. Among its peaks, one in particular stands out, often called South Boisal Mons. This mountain is extraordinary. At its base, it spans well over 100 kilometers in each direction. From the average level of Io's surface, it rises more than 18 kilometers high, about twice the height of Mount Everest above sea level. Its slopes are varied. Some are gradual, others steep, and on one side, there is a towering escarpment, a cliff that falls away by around 15 kilometers in a near-sheer drop. Features like this are unlike anything on Earth. Our planet's stronger gravity and different tectonic style make such extreme, unsupported heights and cliffs difficult to sustain for long. On many other moons and planets, tectonic activity is too weak to raise such dramatic structures in the first place. Io, however, is constantly stressed by tidal forces, and its crust is broken and reshaped again and again. One prevailing idea is that Boe Sole Montes formed when a chunk of Io's outer shell was forced upward and tilted by powerful internal stresses. Imagine a vast slab of crust being pressed and torqued until it broke loose and partially sank on one side, while the other side remained lifted. The raised edge would form a towering mountain front, while the sunken side might be lost beneath layers of younger lava. Over time, landslides, quakes, and eruptions would sculpt the massif into the complex, jagged shape we see today. In the chill of space, Io orbits Jupiter again and again, its bright surface constantly renewed by eruptions, its mountains pushed and broken by invisible forces, its thin atmosphere glowing faintly as it is battered by particles from its giant neighbor. While you lie here under Earth's calmer sky, this distant moon is endlessly flexed and heated, its lava lakes stirred, its plumes thrown upward, its cliffs standing tall over a landscape that never truly settles. If you keep drifting northwest across Io's strange painted surface, the ground beneath you begins to sink and open, as if a great bite has been taken out of the crust. This is Loki Patera, a vast volcanic depression that stretches for hundreds of kilometers, a kind of broken, glowing cauldron on the night side of a distant moon. From above, Loki looks a bit like a ragged horseshoe or a dark, sprawling lake. Its diameter is on the order of a couple of 100 kilometers, and the total area of the depression is larger than many of Earth's great inland seas. But there is no water here, no waves, no shorelines in the sense we know them. Instead, Loki is filled with a lake of molten rock, a deep reservoir of sulfur-rich silicate lava connected directly to the restless mantle below. At the surface, this lava lake does not usually blaze like an open furnace. Io's thin, cold atmosphere draws heat from the uppermost layer of the melt. Piece by piece, the top cools and stiffens into a crust, forming dark plates that float on the glowing liquid beneath. For a while, Loki appears relatively calm, its temperatures measured from orbit settling into values that might sound almost mild, just a few tens of degrees above or below freezing at the very topmost skin. But this calm is temporary, more like a pause in breathing than a true stillness. As time passes, the crust thickens, the cooled plates grow heavier, and the molten rock below continues to move. Eventually, the balance gives way. In different parts of the lake, at different times, the crust loses its support, fractures, and suddenly founders. Chunks of solidified rock tilt and sink, exposing fresh, incandescent lava. A wave of brightening sweeps across the patera over weeks or months as new molten surface appears and then begins to cool again. The cycle repeats on timescales of hundreds of days, like the slow, deep pulse of a fiery heart. We do not expect life, as we know it, to thrive in such a place. Io's surface has almost no water. Its air is vanishingly thin and dominated by sulfur dioxide. Temperatures swing between intense heat near eruptions and brutal cold in the plains. Yet, in the glow of Loki's lava, it is hard not to think about strange possibilities. On Earth, there are hardy microbes that cling to the walls of deep-sea vents, feeding on chemical energy where sunlight never reaches. If anything ever arose on Io, it would have to be even more resilient, drawing energy from sulfur and rock, enduring both intense volcanism and rapid change. For now, such life remains an idea rather than a discovery, and the violent, shifting nature of Io's crust makes even that idea feel fragile. Away from the great calderas and mountain ranges, much of Io's surface is surprisingly gentle, at least in shape. Vast plains stretch out between the major volcanoes, coated in thick blankets of sulfur and sulfur dioxide frost. Seen from orbit, these plains appear as pale, softly colored regions, painted in creams, yellows, and muted reds, with occasional darker stains where lava has intruded. The brightest and broadest of these smooth areas can span thousands of kilometers. If you travel westward from Loki Patera, crossing over scattered vents and narrow lava flows, you eventually arrive at such a region, Media Regio. It is a large, irregular patch of relatively smooth terrain, ringed by rugged mountains and dark volcanic depressions. This bright plateau covers a significant fraction of Io's surface, more than a tenth of the entire moon, almost like a continent of frost set among fields of fire. Most of Media Regio is gently undulating and uniform, but it is not untouched. In places, dark, sinuous lava flows snake out from nearby vents and cut across the pale ground, leaving trails that stand out sharply against the lighter frost. These flows remind us that even here, beyond the most dramatic volcanic centers, Io's surface is still being repaved, little by little. Some scientists suspect that the lithosphere beneath Media Regio is unusually thick and strong, perhaps forming a large, stable block that has resisted being broken apart. In that view, the region might be an ancient piece of crust that has survived relatively intact, while the areas around it have been stretched, folded, and flooded. Others imagine that, beneath the plains, the upper mantle may be cooler and more rigid, with less readily available magma. In both cases, the surface would see fewer eruptions and slower change. Temperatures over the plains are far lower than in the volcanic hotspots. In a place like Media Regio, the ground can sit around 110 Kelvin, well over 100 degrees below zero on the Celsius scale. In such cold conditions, sulfur dioxide gas from the tenuous atmosphere readily condenses, settling out as frost and fine grains, smoothing the small-scale roughness of the terrain. Over time, repeated cycles of deposition and sublimation, freezing and re-evaporation may help maintain the soft, powdery appearance of these regions. As you cross the bright plains and continue northwest, the ground begins to darken again. Ahead lies another important volcano, Amirani. Unlike Loki's vast, somewhat enclosed basin, Amirani is a long, complex fissure system with a patera at its heart and lava emerging from multiple points along its length. From a distance, the caldera itself is not especially immense by Io's standards. What makes Amirani so striking is the network of lava flows that spread out from it like dark rivers, radiating into the surrounding plains. One of these flows stretches northward for hundreds of kilometers, in places many tens of kilometers wide. It is the largest known active lava flow in the solar system, a broad, solidified tongue of once molten rock that crept across the surface over repeated eruptions. Another major flow extends westward, once thought to be a separate feature until better images showed that it, too, is part of Amirani's volcanic system. To the east, a crown of smaller, darker streams suggests episodes of more localized activity, perhaps fed by hidden channels within the crust. Beneath this region, scientists imagine a branching maze of magma conduits and tubes. These underground pathways can carry molten rock away from the main vent, allowing eruptions to break through the surface dozens or hundreds of kilometers from the primary caldera. In thermal infrared images, Amirani glows with intense heat. The central patera can reach temperatures on the order of 1,600 degrees Celsius in its hottest spots, while surrounding flows still retain warmth long after an eruption, cooling slowly into darkness. Over long spans of time, repeated outpourings of lava from Amirani are expected to build up a broad volcanic shield, an elevated, gently sloping mound of solidified flows stacked atop one another. On Mars, a volcano like Olympus Mons rises in just this way, layer upon layer of basaltic lava, eventually forming a mountain taller than any on Earth. On Io, something similar may be happening here, although tidal flexing and continual resurfacing may keep the landscape more patchwork and fractured than on a quieter world. Stepping back from these individual volcanoes, you can feel the larger pattern. Io is small, but it behaves like a world under intense internal stress. For most rocky planets and moons, internal heat comes largely from the slow decay of radioactive elements locked in their interiors. Io, however, is too small to hold much of this heat for long. Its extraordinary activity must be powered by something else. That something is the constant gravitational tug-of-war with Jupiter and its neighboring moons. Io's orbit is slightly elliptical, and resonances with Europa and Ganymede keep it from settling into a perfectly circular path. As Io moves closer to and farther from Jupiter, it is squeezed and released. The moon is flexed by many meters with each orbit, and that flexing generates heat through friction in the interior. It is a bit like kneading dough over and over, except here the dough is rock, and the warmth is enough to keep large regions of the mantle in a molten or semi-molten state. When this internal heat finds pathways to the surface, it erupts as lava fountains, sprawling flows, and enormous plumes of gas and dust. Because Io's gravity is relatively low, material thrown up by these eruptions can rise to incredible heights before falling back. Some particles escape entirely, drifting into space. Others become caught in Jupiter's magnetic field, forming a diffuse torus of plasma around the giant planet. Still others eventually settle onto the surfaces of neighboring moons or contribute to the faint rings that girdle Jupiter. In Io's northern latitudes lies another especially dramatic volcanic complex, Tvashtar Paterae. This region, a cluster of overlapping calderas and vents spanning several hundred kilometers, has produced some of the most spectacular eruptions we have ever seen beyond Earth. Over the past few decades, spacecraft have recorded towering plumes rising hundreds of kilometers above the surface from Tvashtar, their arcs outlined against the black backdrop of space. During one particularly intense episode, a plume shot up to heights approaching 400 kilometers. Its fallout dusted a wide area around the vent with fresh deposits. Another eruption in the same region continued for over a year and a half, sending out repeated blasts of lava and gas. In infrared images, Tvashtar shone as a bright, hot patch, surrounded by cooling flows that slowly darkened over time. Each such event gives us a chance to watch tidal heating in action, to see how magma moves, how vents open and close, and how the surface responds. By tracking the changing shapes of plumes and the temperatures of hotspots, scientists can infer the depth of magma reservoirs, the composition of the erupting material, and the way Io's crust fractures and heals. Even now, new observations keep arriving. A recent close pass by the Juno spacecraft, sweeping just a short distance above Io's tortured surface, captured detailed images of calderas, fissures, and glowing flows. From this vantage point, plumes appear as delicate, ghost-like fans, and the footprints of eruptions can be traced as dark stains across the frosted plains. Future flybys will continue to refine our view, and carefully tuned instruments can perform spectral measurements of Io's thin atmosphere and freshly exposed lava, teasing out their chemical makeup. For the moment, most planned missions favor the icy moons, worlds like Europa and Ganymede, where hidden oceans might offer shelter for life. Io, with its ceaseless volcanism and harsh, dry surface, is harder to visit and less forgiving. Ideas for dedicated missions have been considered and set aside more than once. Yet Io remains a place that quietly tugs at curiosity, a small moon endlessly remade by fire, circling a giant planet under a distant Sunday. While you lie in the dark, listening and breathing in the calm of your own world, this restless moon keeps turning. Lava lakes overturn their crust, frost forms and evaporates on the plains. Plumes light up the edge of the disk like tiny, fleeting fountains. Mountains stand against a black sky, twice as tall as any on Earth. And somewhere above it all, a spacecraft glides past, its instruments open, catching for a moment the glow and motion of a world that never really sleeps. Far beyond Jupiter's restless moons, past the wide path of the asteroid belt, and out into the colder dark, Saturn moves in its slow, stately orbit. Wrapped in its rings, it carries along a family of moons, each with its own quiet story. One of them, almost planet-sized, glows in the faint light with a deep, honey-colored hue. This is Titan. Titan orbits Saturn at a distance of a little over 1 million kilometers, circling the planet in just under 16 Earth days. Its path is almost perfectly circular, steady and calm. In size, Titan is impressive. Wider than the planet Mercury, with a diameter a bit over 5,000 kilometers, but it is far lighter than Mercury. Where Mercury is made mostly of rock and metal, Titan carries a great deal of ice within it, making its average density much lower than Earth's. It is a world built from different ingredients, assembled in a much colder part of the solar system. Deep inside, beneath the hazy skies and frozen crust, Titan is thought to have a layered structure. At the center lies a rocky core rich in silicate minerals. Around that, instead of hot mantle rock like Earth's, there is a vast shell of ice and liquid, a hidden ocean, hundreds of kilometers deep, mixed with water, ammonia, methane, and dissolved salts. Because those ingredients lower the freezing point, the ocean can remain liquid even at temperatures far below water's usual freezing point. Above this ocean sits a thick shell of solid ice and frozen hydrates, perhaps 100 kilometers thick or more. This shell is not perfectly rigid. The tides raised by Saturn's gravity flex and stress it, cracking and shifting the crust. In some regions, this may open conduits from the subsurface ocean up toward the surface, creating cryovolcanoes, places where cold slurries of water, ammonia, and other volatiles can slowly emerge, spread, and freeze, the way lava does on rocky worlds, but at far lower temperatures. On the surface, the air is bitterly cold. Titan sits roughly 10 times farther from the sun than Earth does, and only a small fraction of sunlight reaches it. At ground level, the average temperature is around 94 Kelvin, almost 180 degrees Celsius below zero. At those temperatures, water ice is as hard as rock, but some hydrocarbons are close to their boiling and freezing points. Methane, in particular, plays a role here, similar to water on Earth. A little warming or cooling can move methane between gas and liquid. When the surface is slightly warmer, methane evaporates into the air. When it cools, methane condenses into clouds and falls as rain. Over long times, this simple cycle has carved and filled the landscape. Titan has lakes and seas near its poles, made not of water, but of liquid methane and ethane. It has rivers that twist and branch, dark channels cut into ice rock, and shorelines where waves, if they rise, lap against frozen banks. The atmosphere that supports this weather is surprisingly thick. Titan's air is dominated by nitrogen, with a small but important fraction of methane mixed in. The pressure at the surface is higher than Earth's, even though the gravity is much weaker. Above, sunlight and energetic particles break apart methane molecules, allowing them to recombine into more complex hydrocarbons and organic hazes. Tiny particles of this material hang in the air, forming an orange-yellow smog that surrounds the whole moon. This haze absorbs and scatters visible light, hiding the surface from normal cameras and giving Titan its soft, opaque glow. It also reflects some of the sun's warmth back into space before it can reach the ground, a kind of anti-greenhouse effect that cools the surface by several degrees. Infrared light, however, can pass through more easily. By watching Titan with instruments that see in infrared, and by using radar pulses that can penetrate the haze and bounce off the ground, spacecraft have been able to sketch out the shapes of its continents, seas, and mountains. The Cassini spacecraft, which spent many years orbiting Saturn, devoted a great deal of attention to Titan. With its radar and infrared eyes, it mapped large parts of the surface, revealing bright and dark regions of many shapes. Some reflect a great deal of light and appear pale. Others are dark and smooth, likely seas of liquid hydrocarbons or dunes of organic sand. Near Titan's equator lies a bright region known as Adiri, and, to the east of it, darker stretches, like Shangri-La and Fensal. Just south of the equator, in a bright terrain, rises one of the tallest mountains identified on Titan, Doom Mons. It spans tens of kilometers across and rises roughly 1.5 kilometers above the surrounding plains. Its summit is marked by depressions that resemble volcanic craters, and its slopes show signs of past flows, channels, and lobes that may be the frozen remains of cryovolcanic outpourings. Instead of glowing lava, these would have been mixtures of water, ammonia, and other volatiles, oozing across the frigid ground and then solidifying. Not far to the northeast lies a deep, elongated depression called Sotra or Sotra Patera, thought to be part of the same tectonic and cryovolcanic complex as Doom Mons. The floor of this depression lies significantly below the surrounding terrain, and its walls rise steeply. Together, Doom Mons and Sotra Patera may form one of Titan's most dramatic examples of an icy volcano and its associated vent, an echo in slow motion and low temperature of the fiery mountains on worlds closer to the Sunday. North of these features spreads a dark, rough area, often referred to as Mohini Fluctus, a wide stretch believed to be covered in cryovolcanic deposits. It extends for well over 100 kilometers, narrowing in some places and widening in others. Here, frozen flows and lobes of material alternate with darker dune fields. The dunes are made of small grains of solid hydrocarbons and ice, shaped by Titan's slow, steady winds into long, parallel ridges. If you follow the dark band of Fensol westward and then north, the land changes again. In its northwestern reaches lies Manva, Titan's largest known impact crater. From orbit, Manva appears as a broad, circular ring, hundreds of kilometers across, faintly etched into the landscape. Its floor lies only a couple of 100 meters below the surroundings now, and the ring of hills that marks its edges rises less than half a kilometer above the plains. Manrava is thought to be very old, perhaps hundreds of millions, or even more than 1 billion years in age. Over such spans, erosion and tectonic activity have softened its features. Icy crust has flowed, material has slumped from the rim inward, and deposits from rain, lakes, and wind-blown dust have partially filled the basin. Yet the basic structure is still visible, a central zone of lighter terrain, perhaps uplifted when the impact rebounded the crust, encircled by a moat of darker plains, and then by a low outer ring. It is a ghost of a cataclysm from Titan's early times, preserved and blurred by the gentle movements of a very cold world. Turning southward again, you come to one of Titan's most intriguing features, a bright, curved region known as Hote Arcus. From above, it looks like a luminous arc, several hundred kilometers long, tracing a boundary between rough, higher terrain and a lower-lying plain. Radar data hint that the surface here is unusually smooth in some places and more rugged in others, as if materials with different origins have met and mingled. Parts of Hote Arcus appear to change slowly over time in infrared images, brightening or dimming. One possible explanation is that cryovolcanic activity occasionally resurfaces patches of ground here, laying down fresh deposits that have different reflective properties. These materials might then flow outward into adjacent valleys or slowly evaporate, leaving behind residues that alter the arc's appearance. From orbit, narrow, branching features extend away from the brighter area, faintly resembling dry river channels or drainages. To the northwest of Hote lies a vast, ancient terrain called Xanadu. It is one of Titan's brightest and most complex regions, a highland area thought to be composed of older, heavily eroded crust. Xanadu's surface is deeply cut by networks of valleys and ridges, giving it a rugged, patchwork look in radar images. Its northwestern edge is marked by Mithrim Montes, a set of long, parallel mountain ranges stretching for about 150 kilometers. Their peaks rise nearly 2 kilometers above the surrounding landscape, impressive heights in a world where ice is the primary rock. Between these highlands and the darker surrounding plains, Titan's rivers once, and perhaps still, carved paths, guided by subtle slopes and fractures. Liquids in this cold world don't behave exactly like water on Earth, but they still flow downhill, gather in depressions, spread into lakes, and evaporate back into the thick air. Over time, they shape and soften the land, just as water does at home. Through the orange haze above, sunlight filters weakly down, always dim, never bright. Methane clouds drift and gather, then thin away. In the distance, Saturn looms in the sky as a pale, banded disk, edged with the faint curve of its rings. On the ground, dunes slowly migrate, lakes fill and recede, and icy mountains cast long shadows across frozen plains. From your warm room on Earth, Titan is just a tiny point of light, tucked near Saturn in the night sky. But if you could stand there, wrapped safely against the crushing cold, and look around, you would be standing beneath an alien, yet strangely familiar weather. Clouds, rain, rivers, and seas, all made from different substances, dancing to the same simple laws. While you lie here breathing in easy, temperate air, this distant moon keeps its slow rotation. One face always turned towards Saturn, its hidden ocean shifting gently beneath an icy crust, its hazy sky glowing softly in the dim sunlight, holding its secrets in the quiet cold. If you could somehow stand on one of Titan's southern mountain ridges and slowly climb toward its highest point, the world around you would feel strangely gentle and alien at the same time. That tallest peak rises a little over 3 kilometers above the plains, smaller than some of Earth's grandest mountains. But on Titan, under its heavy sky and low gravity, it would tower quietly over the landscape. From that summit, if you turned and looked toward the west, you would see a vast, dark expanse stretching away for hundreds of kilometers. This is Shangri-La, a broad, low-lying plain of organic sand and dust. Much of it sits below Titan's average elevation and is relatively flat, like the floor of a drained basin. Scattered here and there, paler rises and ridges interrupt the darkness, high spots that may once have been islands, standing above a sea of liquid methane and ethane long ago. Some scientists think that, even now, liquid hydrocarbons might linger just beneath the surface in parts of Shangri-La, the way groundwater stays hidden beneath desert sands on Earth. If you could scoop away the top layers of frosted grains, you might eventually reach materials saturated with methane, cold and slow but still mobile. West of Shangri-La, the terrain brightens into a large upland region called Adiri. In radar and infrared images, Adiri stands out sharply against the darker surroundings, as if lit from within. Its surface is carved by countless narrow channels and branching patterns, a network of old drainage paths etched into the icy crust. These are thought to have been cut by flowing liquid hydrocarbons, rain-fed streams and rivers that once ran down from higher ground, carrying dark particles and carving their way toward lower plains. To the west of Adiri lies another dark area, Belet, a wide belt of dunes and plains. To the east, near the border where Adiri fades into Shangri-La, there is a small patch of ground that has, in a way, become familiar to us. This is where the Huygens probe touched down, the first and so far only spacecraft to land on the surface of a world in the outer solar system. Huygens traveled to Titan as part of the Cassini-Huygens mission, launched from Earth in the late 1990s. The combined spacecraft spent years crossing the cold spaces between the planets. Cassini entered Saturn's orbit in 2004, and a few months later, Huygens separated and began its solitary descent toward Titan's hidden surface. Wrapped in its heat shield, the lander plunged into Titan's thick atmosphere. As it slowed, parachutes opened one after another, gently trading speed for time. Over the course of a couple of hours, Huygens drifted downward through layers of haze and cloud, measuring the winds, temperatures, and composition of the air as it passed. The parachute system slowed it so carefully that, at the moment of landing, the probe was moving only a few meters per second, no harder than a firm jump on Earth. Inside, its instruments were busy. Huygens carried sensors to taste the atmosphere, to measure how easily it conducted electricity, to record sounds, and to capture images as it fell. It watched the orange haze thin and glimpsed darker and lighter patches on the surface below. When it finally touched down, it felt a sharp but survivable jolt, then settled and began to send back data from Titan's surface itself. The first images from the ground showed a dim, muted landscape, a relatively flat plain scattered with rounded stones and pebbles of many sizes. Their shapes suggested that they had been worn and smoothed by flowing liquid, much as rocks in a streambed on Earth are tumbled and polished by water. Huygens also carried a small device to gently push into the ground beneath it. As it pressed down, it found a thin surface layer of small, rounded particles over a firmer, yet still somewhat yielding substrate. The closest comparison might be damp sand or compacted slushy snow, except that here, the wetness came from liquid hydrocarbons rather than water. During this process, the instruments detected methane gas rising from the disturbed soil. It seemed that the ground was saturated with liquid methane, or a mixture of hydrocarbons, and that some of this was released when the surface was pressed and disturbed. For a little while, the lander sat in that alien dampness, quietly sampling and measuring. In total, Huygens sent back hundreds of photographs and a large volume of data. When scientists on Earth carefully sifted through it, they found subtle but important clues about Titan's layered atmosphere. At an altitude of around 80 kilometers, there appeared to be a zone of relative calm, a kind of boundary layer where winds from above and below seemed to fade. It was as if Titan's air were organized into distinct rooms, and this altitude marked the door between them. The cause of this quiescent layer is still not fully understood. The mission also confirmed that Titan has not just one, but two distinct ionospheres, regions where the air is partly ionized and conducts electricity. One lies high above, around 1,200 kilometers up, shaped mainly by the solar wind and cosmic radiation. The other sits much lower, near 60 kilometers, and its origin is less clear, possibly tied to complex chemistry and interactions within Titan's haze. If you leave Adiri and its landing site behind, and let your imagination travel northwest, you eventually come to one of Titan's most striking features, Kraken Mare. This is the largest known sea of liquid hydrocarbons on the Moon, a dark, smooth expanse spanning hundreds of thousands of square kilometers, just a little smaller than the Black Sea on Earth. From above, it looks like an irregular, branching lake with bays, peninsulas, and islands of bright land rising from its inky surface. The exact depth of Kraken Mare is still not fully known, but radar measurements show that in many places it is at least a couple of 100 meters deep, and perhaps more. Its liquid is a cold mixture of methane and ethane, thick and sluggish compared to water, but still fluid enough to lap against shores and possibly carry waves under the right winds. A little to the north lies another great sea, Ligeia Mare. Smaller than Kraken, but still vast. It spreads across a region near Titan's pole, a quiet, dark patch, almost 500 kilometers across. Its area is comparable to that of a large terrestrial inland sea, yet, instead of salt water, it holds liquid hydrocarbons. Instead of sandy beaches, its shores are made of frozen organic sediments and ice. Connecting these seas is a long, narrow strait, a sinuous channel that allows liquids to move between Kraken and Ligeia. Around them, scattered across Titan's polar regions, lie many smaller lakes and inlets. Some are rounded and smooth, like old craters that later filled with liquid. Others have branching, intricate shapes, as if they formed where rivers and channels joined and spread. In 2014, careful analysis of Cassini's radar images revealed something unexpected on Ligeia Mare, a bright patch that had not been there before. Over the course of several observations, this odd feature grew in size, reaching a couple of 100 kilometers across, then faded away again. It was quickly nicknamed the Magic Island, a temporary, shimmering presence on an otherwise dark sea. One idea to explain it is that temperature changes within Ligeia's liquid layers stirred the mixture, releasing dissolved nitrogen as bubbles. In Titan's cold, viscous hydrocarbons, such bubbles could grow relatively large and persist for a long time, forming a frothy layer near the surface. A field of these bubbles would reflect radar signals more strongly, making the area appear bright from orbit. As conditions changed, the foam could dissipate, merging back into the sea and leaving no lasting trace. If we ever send a floating probe or submarine into one of Titan's seas, such foamy patches might complicate its work, interfering with sensors or altering how sound and radio waves travel through the liquid. For now, they remain a reminder that even in the deep cold, Titan's lakes and seas are not perfectly still. An earlier idea for an exploratory mission imagined a dedicated boat or submarine drifting in one of these seas, listening, sampling, and watching the shores roll by. That concept was put aside for a time, but another vision has taken shape in its place, a flying explorer called Dragonfly. Dragonfly is being designed as a kind of large, nuclear-powered drone, a rotorcraft with multiple pairs of blades, capable of takeoff and landing in Titan's thick air. The dense atmosphere and low gravity make flight comparatively efficient there. With the steady power from a radioisotope generator, Dragonfly is planned to hop from place to place, rising a few kilometers above the surface at a time, cruising at modest speeds, and then touching down to study new sites. Its cameras will be able to capture wide views of dunes, mountains, and possible cryovolcanic features, as well as close-up images of rocks and grains beneath its landing skids. A mass spectrometer will examine the chemical composition of gases and solids, searching for complex organic molecules and clues to surface chemistry. Other instruments will measure weather, radiation, and the properties of Titan's frost and sand. Behind all of this is a deeper, softer question. Could anything live in such a place? By the standards of life on Earth, Titan's surface looks deeply unfriendly. The temperature is astonishingly low. Liquid water is frozen solid into rock-hard ice. The atmosphere contains toxic compounds like hydrogen cyanide. Sunlight is faint and filtered through a thick haze. Under such conditions, familiar biology cells filled with liquid water, building proteins, and DNA would struggle to function. And yet, the chemistry is rich. Titan's air and surface are full of organic molecules, from simple hydrocarbons to more complex chains and rings. In laboratory experiments, mixtures of nitrogen and methane, subjected to energy, light, electricity, or particles, produce molecules that resemble the building blocks of proteins and genetic material. On Titan, something like this chemistry happens naturally, over and over, across a whole world. Liquid methane and ethane, although very different from water, are still solvents. They can dissolve other substances, carry them, and allow reactions to happen. Under certain conditions, mixtures of hydrocarbons and other gases might form environments that echo, faintly, the primordial soup imagined for early Earth, only translated into an entirely different temperature and chemistry. If life ever arose on Titan, it would likely bear almost no resemblance to anything we know built from other molecules, moving at slower speeds, its reactions running in a deep, patient cold. So far, we have no direct evidence that such life exists, but the ingredients for complex chemistry are there, and that alone makes Titan a quietly compelling place to wonder about. For now, as you lie here listening, your own world feels warm and familiar, somewhere far away, under a hazy orange sky. Rounded pebbles rest on a frozen plain where methane once flowed like rainwater. Dark seas of liquid hydrocarbons lie still beneath a dim Sunday. A tiny probe sits silent where it landed long ago. And in the years to come, if plans hold, a new flying visitor may descend through that same thick atmosphere, carrying our curiosity with it into the cold, exploring gently while you sleep. Far out in the quiet dark, about 40 times farther from the sun than Earth, there is a small, cold world that moves so slowly you could live your whole life and never see it complete a single lap. This is Pluto. For a long time, it was just a faint, wandering point of light, its details hidden in distance and shadow. Pluto follows a stretched oval path around the sun, taking about 248 Earth years to complete one orbit. Sometimes it comes a little closer in, sometimes it slips farther out. At its nearest, it moves to a bit under 30 astronomical units from the Sunday. At its farthest, it drifts near 50. Right now, it is on the long, slow part of its journey outward, heading toward that distant aphelion it will not reach until the next century. In size, Pluto is modest. Its radius is a little under 1,200 kilometers smaller than our moon, smaller than several other moons in the solar system. Its mass is only a fraction of the moon's. In many ways, it has more in common with the icy bodies of the Kuiper Belt, things like Eris and Sedna, than with the 8 main planets. That is why, in 2006, it was placed at the top of a new category, dwarf planets. Not a demotion in spirit, really, but a recognition that this little world belongs to a different family. From Earth, even through powerful telescopes, Pluto appears only as a tiny, blurry disk, tinted brownish and indistinct. No mountains or valleys show themselves, no clear markings, just a softly glowing speck. For most of the 20th century, that was all we had, a dot in the dark whose mass could be calculated from the motion of its largest moon, whose orbit could be traced, but whose face remained hidden. That changed when a small spacecraft left Earth on a fast outward path. In 2006, the same year, Pluto's label shifted. NASA's New Horizons mission launched toward the outer solar system. It swung past Jupiter for a gravitational boost, snapped some beautiful portraits of the giant planet, then continued onward through the deep cold. After more than 9 years of travel, in July 2015, New Horizons rushed through the Pluto system, gathering as much data as it could in the brief hours of its flyby. The spacecraft never slowed enough to orbit. It simply streaked past, turning its instruments as it went, recording images, spectra, and measurements. In total, it collected several gigabytes of information, more than it could send home quickly over such a vast distance. It took over a year for all of the data to trickle back to Earth, bit by bit, carried by radio waves across billions of kilometers. From those signals, Pluto's blank face suddenly became a world. It turned out to have bright and dark regions, towering mountains, smooth plains, and mysterious pits and fractures. Underneath those features lies an interior that, in broad strokes, we can now sketch. Pluto is thought to be a mixture of rock and various ices. At its center is a rocky core, rich in heavier elements, surrounded by a thick shell of water ice. Water, so familiar to us as a liquid, is frozen into a hard, structural material here, more like stone than ice. Outside that shell lies a mantle and crust, formed from more exotic ices, nitrogen, methane, carbon monoxide compounds that can behave almost like water does on Earth, flowing, freezing, sublimating, and condensing as the seasons and temperatures change. Some models suggest that Pluto's core still retains enough heat left over from its formation and from the decay of radioactive elements to keep part of the water ice shell melted. If so, there may be a hidden ocean deep beneath the surface, salty, rich in dissolved ammonia and other substances, chilled to temperatures far below freezing by our standards, yet still liquid in the pressure and chemistry of that buried world. At the surface, though, Pluto is colder than almost anywhere you can imagine. Temperatures hover around 40 to 60 Kelvin, more than 200 degrees below zero on the Celsius scale. In that cold, even nitrogen can freeze into solid sheets, and methane collects as frost. New Horizons revealed one feature in particular that caught everyone's eye: a bright, broad region on the equator, shaped roughly like a heart. This area is called Tombaugh Regio, after the astronomer Clyde Tombaugh, who discovered Pluto in 1930. Its soft outline stretches across nearly a quarter of Pluto's visible surface, a pale contrast against the darker terrains around it. The western half of this heart is a smoother, almost uncratered plain called Sputnik Planitia. From above, it looks like a vast, light-colored basin, about 1,500 kilometers across, bordered by rougher, higher land. Elevation maps show that Sputnik Planitia lies in a deep, elongated depression, a great lowland filled with frozen nitrogen, carbon monoxide, and methane. Parts of its surface are so reflective that they bounce back the majority of the sunlight that touches them. In close-up images, Sputnik Planitia is not perfectly smooth. It is broken into polygonal cells, each tens of kilometers across patches of ice, separated by subtle ridges and troughs. The pattern resembles bubbling or churning, as if the ice itself is very slowly rising in some places and sinking in others. This kind of structure is what you might expect from convection in a thick, soft layer. Material warmed slightly from below becomes buoyant and rises. Cooler material sinks. On Pluto, such convection would happen over millions of years, but the effect is written across the plane like the frozen imprint of a gentle, endless boil. One leading idea is that Sputnik Planitia began as a huge impact basin excavated when a large object struck Pluto long ago. Over time, volatile ices, like nitrogen, flowed into the low area, collected, and thickened. The extra weight of this ice may have even shifted Pluto's orientation, tugging the basin toward the equator. If there is a subsurface ocean, the heavy basin pressing down on the ice shell above it could help explain why this region sits where it does today. Around the edges of Sputnik Planitia rise ranges of dark, rugged mountains. To the west lie the Hillary Montes. To the south, the Tenzing Montes. Some peaks climb 3 to 6 kilometers above the surrounding plains. Because nitrogen ice is too soft to hold such heights, these mountains are thought to be made mostly of water ice, forming a kind of bedrock. At Pluto's temperatures, water ice behaves like very strong rock, capable of supporting steep, towering structures. South of the heart, New Horizons saw a deep, irregular depression surrounded by hummocky, layered terrain, something like an icy caldera bordered by knobby flows. This area may be a cryovolcanic feature, a place where slushy mixtures of water ice and other volatiles once erupted from below and spread outward, freezing into lumpy domes and ridges. The chemistry of these frozen flows, if we could sample them, would offer precious clues about Pluto's interior and the possible presence of that hidden ocean. The eastern half of Tombaugh Regio, by contrast, is darker and more heavily cratered. Where Sputnik Planitia looks young and fresh, this side of the heart bears more scars, suggesting an older surface that has not been completely resurfaced in recent times. Farther east along the equator, a chain of dark spots appears, large, somewhat circular patches separated by lighter ridges. These are called maculae dark markings, and together they form a string of stains, sometimes informally nicknamed the brass knuckles. Each macula has its own name, often drawn from mythology's underworld figures and night spirits. One of the most prominent dark regions lies to the west of Tombaugh Regio, Cthulhu Macula, a long, sprawling band of low reflectivity terrain nearly encircling part of the planet. It stretches almost halfway around Pluto's equator, a broad smear of deep reddish-brown. Cthulhu's surface reflects only a small fraction of the light that hits it, especially when compared to the bright, icy plains of Sputnik Planitia. The darkness is thought to come from a high concentration of tholins, complex organic molecules, formed when sunlight and cosmic radiation break apart simple gases like methane and nitrogen, allowing their fragments to recombine into heavier, darker compounds. Over long spans of time, these substances accumulate, tinting the surface in shades of red and brown. Not all of Cthulhu Macula looks the same. In some places, the terrain is gently rolling, like frozen dunes or waves. In other areas, it is smoother and flatter. Elsewhere, it becomes more rugged, dotted with craters and low hills. This variety suggests a history of deposition, erosion, impact, and perhaps slow glacial-like flow of ices, all layered on top of one another. If you leave the equator and drift northward, Pluto's landscape changes again. Around the North Pole lies Lowell Regio, a broad, bright, banded terrain. Here, the ground is coated in layers of volatile ices, laid down and removed over many seasonal cycles. Pluto's axis is tipped steeply, more than that of Uranus, so its poles can spend long stretches tilted toward the sun or away from it. When a pole is in prolonged sunlight, ices there can sublimate into the atmosphere. When it faces away, they can condense again. At this point in Pluto's slow orbit, its north pole has been tipped more toward the Sunday. Even though the dwarf planet as a whole is moving farther away, this lighting geometry means that the northern regions have recently received more sustained light than before. Some measurements suggest that Pluto's extremely thin atmosphere, made mostly of nitrogen with traces of methane, has become denser over the past few decades, perhaps because sunlight has been evaporating more nitrogen ice from the polar regions into the air. Over longer timescales, as Pluto's orientation changes and it moves along its orbit, this delicate atmosphere may wax and wane, freezing out almost completely at times and thickening somewhat at others. Pluto's orbit has another peculiarity. It is both tilted and elongated relative to the plane in which the major planets travel. And Pluto itself does not travel alone. It shares a close, intricate dance with its largest moon, Charon. Charon is big, so big that it is more like a companion than a traditional satellite. Its mass is over 1/10 of Pluto's, and the center of mass, the point around which both bodies orbit, actually lies outside Pluto's surface. As a result, the two worlds spin around this shared point in space, locked together by gravity. They are also tidally locked to each other, which means Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto. If you stood on one of them, the other would hang in the same spot in the sky, never rising or setting, only slowly wobbling. Charon's surface is darker and less variegated than Pluto's, dominated by water ice, with patches of other ices mixed in. One hemisphere bears a broad, reddish cap of material, likely tholins formed in a way similar to those on Pluto's dark regions. Cracks and chasms cut across parts of Charon's surface, hinting at tectonic stretching or freezing and expansion in its own interior. Beyond Charon, Pluto has several much smaller moons: Nix, Hydra, Kerberos, and Styx. These are irregular, lumpy bodies, only tens of kilometers across, likely made mostly of water ice. They spin in odd, tumbling ways, not tidally locked, and their orbits are arranged in a set of resonances that keep them relatively stable over long times. Many scientists suspect that these small moons, along with Charon, formed from debris after a large collision in Pluto's early history, or they may include fragments captured from the distant Kuiper belt, gathered into this tiny, faraway system. Now, when you look up at the night sky from Earth, Pluto is still just a faint point, invisible without a telescope. But in your mind, you can carry a different image, a small, complex world with a bright ice heart, dark, ancient plains, towering water ice mountains, and a companion moon circling so closely that the two almost form a double planet. While you rest under a warm, thick atmosphere rich in oxygen, Pluto lies far away in the cold edge of the sun's light, turning slowly, heart-shaped plane facing out into the dark, keeping its secrets in frozen layers of nitrogen and ice. Even with all that New Horizons showed us, a large part of Charon still lies just beyond our detailed view, like a face half hidden in shadow. But on the side we did see, there are already enough strange and beautiful features to linger over for a while. South of the equator, there is a wide, relatively smooth region called Vulcan Planum. Its exact size is still uncertain, but it covers at least a few 100,000 square kilometers, large enough to rival a country on Earth. Here, rising from the gently rolling plains, stands Charon's tallest known mountain, Kubrick Mons. It is about 40 kilometers across, and some estimates suggest it may reach 4 kilometers above the surrounding terrain. Around its base lies a broad, circular depression, like a shallow moat, dropping as much as 2 kilometers below the plains. One idea is that Kubrick Mons might be a kind of cryovolcano. In that picture, icy material once rose from an underground reservoir and slowly piled up into a dome. As the reservoir emptied or shifted, the ground around the volcano could have sunk, leaving the central peak standing high, encircled by a ring of subsided terrain. It is a quiet, frozen echo of volcanoes we know, translated into the language of ice and ammonia instead of rock and fire. North of Vulcan Planum begins a different kind of landscape, Oz Terra, an older, rougher highland broken by countless craters. Between the smoother southern plains and this battered northern terrain lies a belt of great scarps and chasms, as though the crust had been stretched and broken along a vast boundary. The most prominent of these is Serenity Chasma, a canyon about 200 kilometers long and tens of kilometers wide. In places, it may plunge up to 7 kilometers deep. Steep walls cast thick shadows across its floor, making it hard to see what lies at the bottom, even from space. Farther north still, near Charon's pole, New Horizons revealed a dark, reddish stain spread across the surface, Mordor Macula. It spans several hundred kilometers, a cap of deeper color against the paler ice around it. Its origin is still being worked out. One leading idea is that gases escaping from Pluto's thin atmosphere, mainly nitrogen and methane, are slowly captured by Charon's gravity and tend to settle at its colder poles. There, under faint sunlight and a drizzle of energetic particles and ultraviolet light, those simple molecules can be broken apart and recombined into heavier, tar-like compounds called tholins. Over long periods, they build up in the surface ice, darkening it into the reddish-brown patch we see. It is a quiet process, patient and cumulative, written in layers of frost. All of these features, plains, mountains, chasms, and polar caps, are just the beginning of Charon's story. With only a brief flyby and one close look, much remains unknown. We do not yet have full maps of both hemispheres at high resolution, nor long-term observations to watch how light, frost, and shadow move across them with the changing seasons. Meanwhile, New Horizons has sailed on. After its fleeting encounter with Pluto and Charon, it adjusted its course to visit another small object farther out, and then continued deeper into the Kuiper Belt. Now it is tens of astronomical units from the Sun, coasting through a region filled with dust, ice, and faint, distant debris. Its power supply slowly fades. Sometime in the coming years, its instruments will be switched off one by one until it finally falls silent, still moving outward, an artificial comet of metal and memory. Even so, the data it has already sent home will keep astronomers busy for a long time. In those bits and bytes are clues about how small icy worlds form, how their surfaces crack and flow, how their atmospheres breathe in thin cycles of freezing and evaporation. When you think of space, it can be easy to picture only the grand things: blazing stars, huge planets, bright nebulae. But out in the cold, there are also these small, quiet bodies, dwarf planets, moons, scattered fragments that hold pieces of our system's history in their frozen crusts. A crater here, a dark stain there, a buried ocean somewhere deep below. Each is a tiny part of a much larger story. Tonight, while you rest, people all over the world are still turning those pieces over in their minds, comparing maps, adjusting models, and listening to the last faint signals from distant probes. And somewhere beyond the orbit of Neptune, Pluto and Charon continue their slow dance around a shared center of gravity, turning together in the thin sunlight, keeping their secrets a little longer while we learn, step by gentle step, how to read them.